Welcome back to MathYard Institute, where we do all things computational. This is the second part of the queuing theory series that we are doing. And previously we introduced queuing theory and we ended up at the point we were introducing the formulas. Alright, and as per the visibility or the screen, we can see that the first formula is talking about the probability of the system being idle. Alright, and the probability of the system being idle is 1 minus lambda over mu. Alright, so basically what this means is we know that the probability, when you are certain, the probability is 1, isn't it? Alright, so the probability of certain minus the probability of the system being engaged. So lambda over mu expresses the fraction in which the system is being used. Okay, this is a fraction of the system in use. Right, that I think that's better English, isn't it? Lambda over mu is a fraction of the system in use. Alright, so if you remove the time, the time it takes when the system is in use from 1, you remain with the idle time in which the system is not in use. Right, basically that's what that formula means. When we go to the second formula, which is this one, you are just basically looking at the average number of units in the queue. All right, while the third formula is the average number of units in the system. All right, and also you need to be able to differentiate between the average number of units in a system and in a queue. Remember the simple model that we had created where you have a queue, right, and you have a saver here, then you exit the market. So this is the entry point and this is the exit point. All right, this is the service point. Okay, so the first part, this is a queue. All right, this part you are being saved and that part you exit the market. So the average number in the queue expresses the number in the queue. So if you have 2 people or 3 people or 4 cars in a queue, that is this particular one. But if you are dealing with the average number in the system, you are combining everything starting from the queue to the service point. All right, those that are being saved and those that are in queue combined is basically what that implies. All right, then you go to average time in a system, average time in a queue, and so on. All right, those are our basic formulas that we build our fundamentals on. Remember, we rely on 2 assumptions: that our arrival rate and our service rate are coming from a Poisson distribution, or they are governed by Poisson theorem, right? And also that they are exponentially distributed. Okay, so we have an example on the screen. Given arrivals at a telephone booth are considered to be Poisson at an average time of 8 minutes, all right, between one arrival and the next. So between one arrival and the next, the interval is 8 minutes, all right, full stop. The length of the phone call is distributed exponentially with a mean of 4 minutes. All right, so the service time in this case is 4 minutes. It takes 4 minutes for a telephone booth to keep to maintain a call, right? To keep a call. So the call is on an average of 4 minutes. While For a client to call, all right, it takes 8 minutes from one client to another. All right, so meaning there are some gaps that are there, isn't it? All right, if we are just looking at it from the shallow point of view, we know that if it takes 4 minutes for one call to end, then there's a gap of another 4 minutes for the next person to call, isn't it? All right, but now how do we actually mathematically solve this? All right, we haven't yet looked at the problem. The problem says determine the expected fraction of the day that the phone will be in use. All right, I think I explained briefly about that. Then B says expected number of units in the queue and the expected waiting time in the queue. C, expected number of units in the system. Then D, which was supposed to be D, expected waiting time in the system. All right, so we start with the first one, expected fraction of the day that the phone will be in use. All right, so now we want the fraction of the day where the system is in use, or the phone in this case, which is the server, is in use. Now we go back to our formulas. So the first formula, remember, gave us a probability of idle, right? And we say idle is 1 minus the busy time. Now we want the busy time, so basically we just get this part. You ignore the 1, right? So you just get, then your formula will be lambda minus mu, isn't it? Or your average arrival time minus your service time, or divided by your service time. All right, so what do we have? So we are saying then the formula will be lambda over mu, isn't it? Okay, but what is lambda and what is mu? So let us calculate those. So how do we then calculate? We start with lambda. How do we calculate lambda? So what is lambda in this case? How do we define it? We know that lambda is the average number of units per given time. All right, per given time. Now what have we been told? We are told that it takes an average of 8 minutes between one arrival and the next. So between one call and the next, it takes 8 minutes. Now we need to standardize this, all right? What others in science we call SI units, right? And the standard is hours. So if our standard are hours, so how many calls do we take in an hour? If it takes 8 minutes per call, per call to come, right? How many calls then will we have in an hour? Basically, we say if it takes one call in 8 minutes, how many will we have in 60 minutes, right? So we know that 60 divided by 8 is 7.5. Okay, so therefore our lambda is 7.5 per hour. All right, what about our mu? Our mu, which is the service time. We've been told that our service time is 4 minutes, isn't it? The length of the phone call is distributed exponentially with a mean of 4. All right, so it's service time, meaning it's the time that you are interacting in order to save a client during a call. All right, so if it takes 4 minutes per call, if it takes 4 minutes, all right, what is the average service time in an hour? All right, if one call takes 4 minutes, how many minutes will there be in 60 minutes? All right, we know that So basically we're just going to divide 60 by 4, and that will give us 15, isn't it? 15 per hour. So this is the amount of time we are going to be engaged in an hour. All right. All right. Now, given our mu being 15 and our lambda being 7.5, then we can apply this particular formula, isn't it? Our lambda is 7.5 divided by 15. Okay, what is 7.5 divided by 15? This is 0.5. All right. So that is so the fraction of the day that will be engaged will be 0.5. Or in other terms, it is a half a day, right? If your day is 8 hours, right? 9 to 5, all right? If your working hours are 8 hours, this basically means that you are going to be engaged half the time, all right? And half the time you are going to be idle, right? Quite simple, isn't it? All right. Let's follow the next video to actually start solving B, C, and D. All right. See you in the next video.